Welcome to chapter number 3. This is a summary lesson. This is not to replace the lecture lesson. It's only to reinforce and help in your study. In chapter 3 we will talk about organic compounds, alkanes, and their stereochemistry. We will talk about functional groups, alkanes and alkyne isomers, alkyl groups, naming alkanes, properties of alkanes, conformation of ethane, conformations of other alkynes, a deeper look in gasoline. Okay, alkanes basically, his main characteristic is that relatively are unreactive and are not often involved in chemical reactions. Are a useful vehicle for introducing some important general ideas in organic chemistry if we will name this organic compound that is the base for the naming of organic compounds. And finally we will talk about three-dimensional aspects of these molecules. If we talk about functional groups, a functional group is a group of atoms within a molecule that has a characteristical chemical behavior. Given functional group behave in nearly the same way in every molecule that it's part of. Here we have, for example, a functional group that is a double bond in two different environments, two different molecules, and here we can see how the reactivity is quite similar. If we create one, as you can see here, one double bond with bromine, what we have is the dibromination, the same than here. Okay, that means that functional groups behave more or less the same in any molecule. What happens with carbon-carbon multiple bonds? We saw that we have three types of carbon-carbon multiple bonds. One's a double bond, as you can see here, triple bond, and we can have also aromatic compounds that has its own reactivity. All these structures contain carbon-carbon multiple bonds that, as I defined it before, double bond, triple bond, and alternating double and single bonds. Functional groups that are bonded with carbons that are electronegative atoms. For example, alkyl halide is a halide, fluorochlorobrom iodide, that is bonded to a carbon. Alcohol, OH, that is a hydroxyl group that is bonded to a carbon, oxygen in the case of the ether, or a phosphate group in the case of a phosphate. Here we have more like amine, thiol, sulfide, and disulfide. Also we can have functional groups that are carbon-oxygen double bond, like carbonyl groups, aldehydes, ketones, carboxylic acids, esters, thioesters, amide, and acid chloride. You need to remember these structures because these structures are the most important functional groups that we will saw this year. Okay? In a molecule given, you have to be able to determine which is his functional group. Okay? For example, in this exercise that I recommend to do at home. Alkanes and alkyne isomers. By joining 3, 4, 5 or even more carbon atoms with CC single bonds, the large family of molecules called alkanes could be generated. Here you have an example. For example, with one carbon it's methane, two carbons ethane, three carbons propane, four carbons butane. These are called alkanes that don't have any other functional group are called or described as saturated hydrocarbons, and follow the formula. The number of carbons the number of hydrogens is equal to 2 times the number of carbons plus 2. We can have a straight chain alkanes or normal alkanes, and isomers are compounds that have the same numbers and kinds of atoms but differ in the way the atoms are arranged. That means the matrix of the bonds of the molecule are different. Here you can see, for example, butane is 4 carbons in a row. 2-methylpropane, you see that has this form of a Thai fish. Okay. Also, we can have different functional groups only changing the position of the atom of the bonds. For example, ethanol is an alcohol, while dimethyl ether is a ether. But these two compounds are isomers because they have the same constitutional formula. They say the same molecular formula. Okay, the same that isopropyl and propylamine. Both are isomers because they have the same molecular formula. Compounds that have the same molecular formula but they are connected differently, that means the matrix bond is different, are called constitutional isomers. Here you have several examples: butane, isopropane, or isopropylamine, propylamine. Okay. A compound at the same time can be represented in different ways. Normally, what we do is to represent in the way that is down to the right, okay, CH3, CH2, CH2, CH3, but also can be represented by grabbing all the atoms possible, carbons and hydrogens, in a linear way or in an angular way, or with dashes, or even contracting if we repeat several units in the molecule. Okay, all are valid. What is an alkyl group? An alkyl group basically is a molecule, is a part of a molecule that is bonded to the carbon main chain. And what we do is to remove one of the hydrogens. Here is, for example, CH4 is methane, but if we remove the proton, this is called methyl. And this is called methyl alcohol or methanol, and this is called methylamine because we have this fragment. When an alkane is the main chain, we finish the name with ane. For example, methane, ethane, propane, butane, or pentane. While when it's an alkyl group, it's a substituent, we remove the ane and we put il, methyl, ethyl, propyl, butyl, and or pentyl. Okay? Here we can have some branched groups synthesized from branched alkanes. The important thing is that this is called isobutene. When it's an alkyl, it's isobutyl, and when we have this that is bonded by this carbon, but this central carbon, this is called terbutyl. Okay. We can define a primary carbon as a carbon that only has one substituent. That must be a carbon or a heteroatom, not a hydrogen. Secondary carbon is when this carbon is bonded to two hydrogens. Tertiary, when we only have one hydrogen. And quaternary carbon is when it's bonded to 4 other carbons or 4 other heteroatoms. Okay? How we name the alkanes? Well, we have to apply the International Union of Pure and Applied Chemistry, the UPAC. Okay, and basically what we have is a locant. Where are the substituents? A prefix. What are the substituents? A parent. What is the main chain? A suffix. What is the primary functional group? This is normally how it's following. Okay, and we will follow several very well-defined steps to find the name of the compound. The step 1 is find the parent hydrocarbon. We have to find the longest continuous chain of carbon atoms in the molecule and use the name of that chain as the parent name. If two different chains of equal lengths are present, choose the one with the largest number of branch points as the parent. Step 2, we define the number of the atoms in the longest chain, beginning at the end nearer to the first branch point number in each carbon. If there is branching an equal distance away from both ends of the parent chain, begin numbering at the end nearer of the second branch point. Step number 3, identify and number the substituents. Assign a number or locant to each substituent to locate its point of attachment to the parent chain. If there are two substituents on the same carbon, give both the same number. There must be as many numbers in the name as there are substituents. Step 4, write the name as a single word. Step 5, name a complex substituent as thought if were itself a compound. Okay, we will check how we can do it. Here we have this compound. As you can see here, I check the longer chain possible. The longer chain possible is here 1, 2, 3, 4, 5, 6. Anything that I will choose will be a minimum 5. That means that this has to be the main chain. That means from here I know that it's a hexane that has a substituent in position 1, 2, 3. Why in position 3? Because if I start numbering for the other carbon, what I will get is position 4, and I always need to get the lower number possible. Here we have a 1, 2, 3, 4, 5, 6. In this case, we can calculate that the longer chain is this. If we take this, it's exactly the same that take this. Okay, and then what? We have 6, and we have methyl in second position and ethyl in third position. Take a look of this. This is the main chain. If I make all the combinations, is 1, 2, 3, 4, 5, 6, 7. Where I have a methyl at 3 and ethyl at 4. If I do the numbering opposite, I started from this carbon. As you can see, I will have the ethyl at 4 and the methyl at 5. That means higher numbering than not as it is now. Take a look on this. This is 1. This is the main chain. Will be 9. And the numbering will be 1, 2, 3. The ethyl in 3. The methyl in 4, and then another methyl in 7. If I do the opposite, I get a methyl at 3, a methyl at 6, and an ethyl at 7. That means 1, 4, 7 is smaller than 3, 6, 7. This is the reason why I start numbering from here. 3, 4, 7 is smaller than 3, 6, 7. The substituents, I have a ethyl, a methyl, and another methyl. How I will write this? Always by the substituents goes by alphabetical order. Ethyl first and methyl, because it's E and methyl is M. And then will be 3 ethyl, 4, 7, because the substituent is the same. Dimethyl, I have 2 methyls. To say that I have 2 methyls is dimethyl. No name, because the main chain is a no name. It's 9 carbon chain. For example, here, I check first, we need to check the longer chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the longer chain. You can test it, but it's the longer chain. Then when I have here, I have a substituent in this carbon, a methyl in this carbon, a methyl, and in this carbon I have a methyl propyl. Okay? Or I can say isopropyl. It's depending how good you are in the nomenclature. But both are correct. Then I can start numbering for this carbon, or I can start numbering for this carbon. Obviously I will start numbering for this carbon because here I have a substituent in 2, a substituent in 3, and the other substituent is at 6. If I start here, the first substituent will be 1, 2, 3, 4, 5. That means the numbering is lower starting from here. Then I have 2 methyls and 1 methyl propyl. Obviously, by alphabet, methyl is going first than methyl propyl. That means that I have 2, 3 dimethyl, because I have 2 methyls, 6 2 methyl propyl decane, because are 10 carbon chains. Okay? This type of groups sometimes has his own name that we can use. In this case, methyl propyl, we can say isopropyl. In the case of 4-member ring, if it's like this, is a sec-butyl. If it's like this, isobutyl, and if it's like this, it's a terbutyl. Okay? And remember that the only name that is counting is the butyl, not sec, tert are not. Okay, here you have some exercise to do at home. Properties of the alkanes. Alkanes show, as we saw before, little chemical affinity for other substances and are chemically inert to most laboratory reagents. Okay? Basically, the most common reaction for alkanes is burning. Like paper, like benzene, etc. We have, for example, methane. This is a reaction that is done in the kitchens, in the old kitchens with gas, natural gas. Methane plus oxygen give us CO2 plus water plus energy. It's an exothermic reaction. Okay. Also, we can consider some radical reactions based in light, where we can generate, for example, chloromethane or dichloromethane or trichloromethane or even tetrachloromethane, depending of how many times we do a reaction. We can substitute one hydrogen for a chloride. Between two molecules of alkane, for example, methane, the only force that is attracting these two molecules is the dispersion force. what is the dispersion force? Basically, the dispersion force, or Van der Waals force, or London force, has different names depending of the book, depending of the time, depending of a lot of things. Okay, are induced dipoles. Okay, I imagine that basically an alkane is a chain of atoms that is surrounded by an electronic cloud. Where are the electrons? Isn't it? For luck, for statistic, we can have an excess of electrons in some part of this cloud. And then what we're generating is a negative charge, a partial density charge in some part of the molecule. If there are some density negative charge in some part of the molecule, because simply 2 electrons are in this area, in other area we need to have a positive density charge. This is a dipole, is what we studied in the last lectures. This is a dipole. These dipoles are not real dipoles because basically are determined by statistics, are determined by luck. Means it's something that are very weak and creates not so often. That means these are the dispersion force. These created dipoles in a given molecule. That means that the attraction between 2 hydrocarbons, 2 alkanes, will be very low, but will increase when bigger is the electronic cloud. When bigger is the molecule, more opportunities to create these dipoles, isn't it? Then what we will show is that the melting point and the boiling point is increasing with the size of the alkanes. That means methane is a gas, ethane is a gas, propane is a gas, butane is a gas, but if we are going up, octane is liquid, and if we are going over 50, probably we can have some compounds that are solids. Okay, here you have an example. Pentane boils at 36.1, isopentane at 27.85, neopentane is at 9.5. That means it's depending of how big is the molecule. If you have a branched hydrocarbon or a branched alkene, obviously the surface or the volume will be lower, and then for this reason the boiling point and the melting point will decrease, as you can see in this list. Pentane, isopentane, neopentane. When more branched it is, lower is the boiling point. Why? Because simply the volume is smaller. When more volume has alkane, more induced dipoles can be created, and more interaction force will be. Okay, then we go to the conformations of ethane. Stereochemistry is the branch of chemistry concerned with the three-dimensional aspects of molecules. Rotation is possible around carbon-carbon single bonds in open chain molecules. That means a carbon-carbon bond has free rotation. That means when we draw ethene, if we put our eye across the carbon-carbon bond in the same direction than the carbon-carbon bond, we can see that we can saw this, where the hydrogens of the first carbon are in the holes of the hydrogens of the second carbon, for example this, or we can see the opposite, that the hydrogen of the first carbon are just in front of the hydrogen of the second carbon. These are two rotations of the same molecule, and they are called conformers. That is coming from conformation. The most stable position, as you can imagine, is this, the staggered position, when we have the hydrogens of the first atom alternating the holes of the hydrogens of the second atom. Okay, why? Because basically we don't have any steric interactions between these two. The most unstable conformation, or the less stable conformation, is the one that is eclipsed, where we have one hydrogen in front of the other, because it's when we maximize the steric effects. Okay, that means the two hydrogens are crashing because they are closer. Also, we can define the torsional strain. Okay, that is basically this. Here we have the graphic between the energy and the rotation of the ethane. Okay, here we start with a, for example, eclipsed conformation. We know that is a maximum of energy. Okay, then simply we are rotating, for example, the second atom towards the first. We are rotating very few, and the energy is decreasing until we arrive to a staggered formation, where this hydrogen, as you can see here, is in the middle of the two hydrogens of the first carbon. This will be a minimum of energy. If we continue rotating this bond, what is happening? This is coming to be eclipsed by this hydrogen. We are increasing the energy until we arrive to a maximum. Like the molecule is the same, that means this and this is the same, we will have the same energy that we had at the beginning. And again, rotating, a staggered position, we rotate again, we arrive eclipsed position, we rotate, staggered, we rotate, and we arrive to the starting eclipsed position. Okay, that means when we draw the energy diagram of a molecule regarding the angle of a bond, we always go from staggered minimum energies to eclipsed maximum of energies. Of course, if we have different substituents in each carbon, the relative energies will be different. That means one will be bigger than others. But always a staggered position will be a minimum, an eclipsed position will be a maximum. For example, we complicate a little bit, we put a metal. Okay? In the case of a metal, what we have is that the staggered propane, as you can see here, where each substituent of the first atom is in the middle of the substituents of the second. And if we rotate, what we have is an eclipsed propane, where the metal is eclipsing the hydrogen and the hydrogens are eclipsing the hydrogen. What happens if we increase a little bit the difficulty? Now we put one carbon, that means one metal in the first carbon and one metal in the second carbon. Okay? Now we have different conformations. We have the anti-conformation, where the two big substituents of the first atom and the second atom are in anti-periplanar or anti-conformation. That means 180 degrees one to the other. In this position, obviously, is the position that presents less steric hindrance, because the two big groups are far away as much as possible. This will be the least energetic, the most stable conformation. Will be a minimum, but this minimum will be the maximum minimum. I mean, the minimum with the lowest energy. Okay? And just the opposite, when we have that this is rotating, here we have the CH3 over a hydrogen, but when we have the other staggered position, this staggered position, that we will say gauche, is less stable than not the anti, because now we have some steric strains between this metal and this metal. Here, because one and the other in 180 degrees, they don't see each other, they are as far away as possible, we don't see any interaction. But now, because they are closer, they are only 60 degrees one of the other, we have some static interaction that makes this position unstable. And we have a static strain. If we continue the rotation, what we can find is that we have this diagram. Here is the minimum, that is when the CH3 and the CF3 are in anti, and then we are rotating. Here we have a eclipsed position where each CH3 is in front of a hydrogen. This is a maximum. Then we go down, and we got a minimum, that is this minimum, where the two CH3s are 60 degrees one of the other. Is a minimum, but has more energy than not the anti-conformation, because this is a gauge conformation. Then we are rotating, and now we have the maximum energy, that is the syn conformation, as you can see here. Why? Because now we have eclipsed the two big groups. This is the worst situation possible, when we have eclipsed the two big groups of each carbon. And this will be the maximum of energy, as you can see here. We rotate again, and what we get is another gauge, eclipsed, and finally we come back to the anti-conformation. Okay, that what we know, that the anti-conformation is the lowest energy possible, the syn conformation is the highest energy possible. And then if we want to do mathematics and we want to calculate the energy, we can do it knowing the energy of the torsional strains, mostly torsional strains, torsional and steric strains, and steric strains. When we have a HH eclipsed, it's called a torsional strains, and the strains is around 4 kilojoules. If we have a hydrogen and a metal eclipsed, it's around 6 kilojoules. If we have two metals eclipsed, it's around 11 kilojoules. And we have a CH3 that are gauge are around 3.8 kilojoules. We sum all the positions, and we can know more or less the energy of each conformal. Okay, but as a general rule, anti always is the lowest energy, syn always is the highest energy. Remember, anti is when the two substituents are, the two big substituents of each carbon are 180 degrees one to the other. Syn is when the two big substituents are in an eclipsed position. Okay, that's all. Thank you very much for your attention, and see you in the next lesson.